outside of time. Sand, rock, crystal, wind. The physical world. Nothing in the physical world ever remembers anything. Nothing in the physical world ever anticipates anything.
My, how time flies.
When you're having fun.
Time and time again.
Time is right. What time is it?
Universal time, 6 hours, 17 minutes, 25 seconds.
Time, what is it?
St. Augustine wrote, "What then is time? If no one asks me, I know. But if I want to explain it to someone, I do not know." There is a time that is felt and a time that can be measured by science. Did time have a beginning? A very old question indeed. How can we imagine a world before time began? If we count backwards beyond the clock, beyond the calendar, beyond magnetic drift and radioactive emission, 3.5 billion years, we arrive at our own beginning. The dawn of life on Earth. Science has a word for it, biogenesis. The birth of life. With life, nature created a new kind of time. More advanced, more evolved than the time of the physical world. Memory and expectation provided us with a competitive advantage. Memory and expectation gave birth to the concept of a past and a future. Flash forward 3.5 billion years. Humanity rules the Earth. Humanity is wrapped tight in ticking time. We use time to measure motion. We use motion to measure time. A clock measures time, but time exists without clocks. Time ticks on towards the unknown. Most of us, when we think about time, do so with some hesitation. Time is at once familiar and also a stranger. Most of us don't think about time, except when we're late, which seems to be most of the time. In physics, space is represented as 3 dimensions. Time is represented as the 4th dimension. To describe time, we are often asked to think of objects in motion. For instance, time has been compared to the cable that drives the quaint cable cars of San Francisco.
The cable car attaches itself to something that's hidden, something that you do not see, something that's to an extent mysterious. It is moved by some machinery. You don't know the machinery, you don't even see the cable. It just moves you along, takes you on a ride.
At birth, we are clamped to a buried cable, time, and at death, cast loose from its passage.
For some reason, you didn't recognize
In those first moments of life, the newborn knows no time. Their awakening minds only remember the mother's heavy pulse in the womb. Time has no meaning, but the newborn already depends on clocks, cellular clocks. Biochemical changes that repeat in cycles have been marking time since the moment of conception. Cellular clocks are found in all plants and animals. This is eye surgery being performed on a squishy sea creature called Aplysia californica, if you're a Latin lover. It is a difficult procedure. The researcher must correctly implant a tiny sensor in the animal's optic nerve cell.
The reason we study this animal is that it has a relatively simple nervous system with very large nerve cells. This allows us as neurophysiologists to study the mechanisms of circadian rhythms of biological timing in a relatively simple animal.
Circadian rhythm? More Latin. From circa, Latin meaning about, and dies, Latin for day. Circadian, about a day. A chart recorder has been hot-wired to the wire buried in the eye of Aplysia californica. The needle flicks, not because the animal is seeing light. The needle flicks because it has detected a rhythmic beat in the optic nerve cell.
The eye of the animal actually contains a biological clock. It's like an alarm. It initiates activity in the animal near dawn. Sunlight sets the biological clock. It sets the clock to Virginia time, but it's actually the clock that controls the behavior.
Some very strange hybrids have been created in the biological timing lab to help scientists investigate the chemistry of cellular clocks. The DNA material responsible for the glowing fire in fireflies has been extracted and spliced into the genes of certain common weeds. Insect DNA now controls a plant's cells. The result? A weed that glows in the dark. Great for insomniac gardeners. But there is a serious scientific quest underway here.
What it allows us to do is look right inside those plant cells, and instead of destroying those cells to measure biological function, we can merely measure light output from those cells. So we can look and see how plants grow, divide, and develop without ever interfering with their tissues.
Sensitive electronic cameras can detect the glow, which is not bright enough for our eyes. The weed brightens and darkens over the period of a day. When the plant cells are active, the firefly gene kicks in and its leaves glow. When the plant rests, the leaves dim out. The light level tells researchers in effect whether the weed is awake or asleep.
Sunlight comes in cycles of light and darkness, and a plant is going to have an adaptive advantage if it can anticipate when dawn is coming and anticipate when dusk is coming, rather than merely responding to dawn and dusk.
Cellular clocks often follow a cycle close to the 24-hour day. But as with any clock, it still needs to be set. Some species, such as the iguana, have a light-sensitive organ on the top of their heads that apparently serves to reset their circadian clocks.
Well, the animal has a parietal eye, a third eye, on the top of its head, as do many lizards, which is right up here. He certainly can tell the difference between light and dark with that eye, and probably can discriminate different wavelengths. You can tell short wavelengths from long wavelengths, blue light from red light.
Humans also have cellular clocks, very complex clock systems that help determine how we live out our days.
I happen to be a morning person.
No, you like to go to bed late and get up late.
Get up at 7 and go to bed at 11. Does that make me a day person?
I'm a night person.
I have absolutely no rhythm. It's one of the things that drives Michelle insane.
Well, right now, of course, I've got an internal clock running, and it's set to wake me up between 6:30 a.m. and 7 a.m.
But I actually like to go to bed late and wake up early. So I'm kind of a night-morning person.
In a series of experiments 30 years ago, German researchers placed volunteers in soundproof, light-proof bunkers where they were isolated completely from any exterior time reference: sun, moon, clocks, TV, and radio. The result, most people fell into a daily cycle slightly longer than 24 hours. Apparently, some inner clock kept their routine constant in spite of the fact they had no reference to the actual time of day. One surprising result, a small number of people, about 5%, fell into a cycle of 32 hours, not 24. When they emerged, they had lost weight and were confused. The calendar date was weeks later than they had supposed. Most of us don't live in isolated German bunkers. As young children, we begin life with a strong internal beat. Eat, sleep, wet, cry. Then, at the age of 2 or 3, our awareness of an external beat begins to expand towards understanding time and the world around us.
It's a Power Ranger watch. Okay, 1, 2, 3. They just go the same. Well, you never know. Those might not be magnetic. They might
Slowly, but quite perceptibly, the young child learns the rhythm of life. With each sunrise and sunset, he adapts himself more intimately to the enduring and to the changing aspects of his environment. As the seasons pass, he begins his lifelong search for personal identity. Personal identity becomes intelligible and communicable to others because of the existence of a subtle, private, and communal understanding of an ordering principle. This principle or knowledge, couched in terms of an idea called time, is a central concern to all humans.
By the time we reach adulthood, our circadian rhythms have merged into the heavier beat of societal time. Time was when time seemed different, not so organized. Time was when time seemed kinder, gentler. At the point in history when Homo sapiens became socially aware, time was considered to be cyclical, day and night. The seasons, birth, death, cycles within cycles. The cyclical view of time was quite literal. When Socrates was ordered to drink the poison hemlock, it was assumed that this event and all events would happen over and over. The Hindu religion has viewed time much the same way for 4,000 years. A series of cycles within cycles that makes the experience of time insignificant. By emphasizing timelessness as the ultimate reality of the world, Hinduism reduces the anxiety created by the knowledge of time. The metaphor of time in Buddhism is the wheel of righteousness. Buddha taught that if a person follows the correct path, after many transmigrations, the soul will reach nirvana, a timeless state. In ancient Judaism, time was cyclical. Then a change occurred in the 9th century BC. The ancients traced Hebrew history from creation to Abraham's proof of faith to the promised land, salvation history. History ceased to be just one repeating cycle and became instead a series of events that progressed from a well-defined beginning to an appointed goal. Salvation history, the idea of linear time, was born. Christianity later adopted this salvation history as the foundation of its own doctrine. Birth, life, death, and resurrection. Then another fundamental change tied to religious thought. What became known as the Rule of St. Benedict in Western Christianity would profoundly change the daily routine. Church services would be held at specific times during the day. Timeliness was next to godliness. Then at some point in the 13th century, a sound broke the quiet of the villages. It has never stopped.
They couldn't depend on natural events because the so-called Matins prayer was recited before sunrise. So you had to have some way to get up in time.
The lives of the monks began to revolve around the clock. Sleeping, eating, working, praying, all ordered by the bell, the chimes of time. The day had now been divided into smaller, equal parts. Sunrise and sunset no longer sufficed. Sundials marking time by casting a moving shadow were quickly becoming a bad investment.
Here we have a sundial, a very wet sundial today, so we can't use this instrument as a measure of time duration. We have to use a mechanical clock. This is the reason we invented mechanical clocks, to help us measure time when the sun is not present in the sky.
Oh, I love the sound of ticking. It's kind of music to my ears, really. I know some individuals that cannot live with the ticking of a clock. It reminds them that they are coming nearer and nearer to the end of their life.
It's fortunate for John Shawcross that he can take that ticking and keep on fixing. His job is to keep all the clocks in good repair at the Time Museum in Rockford, Illinois. The museum is located near the interstate in the basement of the Clock Tower Motel. Not such an impressive setting, perhaps, but a very impressive collection. There are, for instance, twittering bird clocks. There is a chariot banquet clock bearing the god of beer. And if you sniff the air here, you might occasionally catch a waft of fragrance from an antique incense clock. Different powders deliver different smells to mark time's passage.
I think this watch, for example, would grace a stylist's idea of what a watch ought to look like today, and would sell very, very well.
Two antique watches with a curiously modern design were handmade by the master, Abraham Louis Breguet, around the time of the American Revolutionary War. The museum in a motel contains a brief history of time, or to be more precise, a history of timekeeping. The pendulum revolutionized timekeeping. With a weight swinging in near-perfect repeating arcs, the pendulum divided up time into precise, equal segments. The Dutch astronomer Christian Huygens was the first to set a weight swinging in a clock in 1656. Prior to the pendulum, the clunky mechanical tick-tock in a clock might vary wildly by as much as 15 minutes a day. A pendulum could narrow the error down to 15 seconds a day. Just in time, too. there was increasing demand for accurate timekeeping. Rural people were streaming into the cities of Europe as the Industrial Revolution began to fire up.
As soon as you start getting urbanization, cities and so on, the cities also have to pay strict attention to time. Too many people, too small a space, they have to find ways to organize activities. Now we open the market, now we close it. If they couldn't keep track of the time and order things by time, they were going to run into trouble just keeping the city operating efficiently.
As increasingly accurate clocks became available, a few explorers began to dream of using timekeeping to improve the accuracy of navigation on the high seas. For centuries, navigators had been able to determine how far north and south they were, the latitude, by observing the sun's angle. In the Arctic, for instance, the navigator would observe that at those high latitudes, the sun was very low on the horizon at noon. But for a navigator to know where on the edge of the Arctic ice cap he was stuck, east or west longitude, he would need an accurate clock. The clock kept the time of the home port.
I just checked the sun's position and found out that it's 12 o'clock here. By this watch I've carried ever since we left England a month ago, it's 9 o'clock in Greenwich. So, our position is 3 hours or 45 degrees east of Greenwich.
Where does that put us?
In Baghdad, sir.
Baghdad?
The problem was obvious. On the rolling deck of a ship at sea, a swinging pendulum would destroy the clock. In 1714, the English Parliament offered an award of £20,000 sterling to anyone who could build a clock that would keep accurate time out on the ocean. That was a lot of money, about 12 million in today's dollars. It attracted the attention of a village carpenter who traveled down to London and announced he was going to try for the prize. His name was John Harrison. One had to be a jack of all trades to make a living in a remote English village. Perhaps that's why John Harrison managed to create the world's first marine timepiece. A replica of it, the Harrison No. 1, ticks away in the Rockford Time Museum.
To overcome the rocking of the ship, he devised a different kind of pendulum, some bar balances. As the ship rocked one way, the balances would counteract each other as they swung to and fro. And this was very effective.
Rather odd, the Harrison No. 1, an ungainly thing. Apparently the inventor thought so too and immediately began trying to make a better, smaller version. He succeeded, but it took John Harrison his entire life to perfect the first seagoing clock.
Harrison's great contribution was really to break the shell of people who said you cannot do it with a timekeeper. And he said you could do it mechanically, could solve this problem mechanically. So it was an enormous breakthrough. And one of the remarkable things is that by 1790, the marine chronometer, as it was developed then, was so sophisticated that right through the Second World War, the basic design of the machine remained almost identical.
Improved navigation enhanced European power, spreading the Industrial Revolution. The age of steam had begun, and arteries of iron linked distant communities into one. At first, villages and towns along the track continued to run on their own time. It might be 2:30 in one place and noon just down the line. Local citizens might have wanted to set their own time, but to do so meant very scary train trips and close encounters of the worst kind. Schedules had to be synchronized properly. A new concept emerged: time zones. For train dispatchers, hours were important, but the minutes were crucial. With the new time zones, it was always the same minute before or after the hour, no matter on which side of the zone one lived. New industrial processes demanded discipline and synchronization.
mechanical clock, for all of its aesthetics and all of its humanity and its making and its care and so forth, is nothing compared to the modern atomic clock.
Of course, mechanical clocks can't measure up when it comes to accuracy, but they have not been relegated just to museums. The sound and feel of mechanical time still holds an attraction for millions of people. In small shops scattered around the world, clockmakers like Leland Smith refuse to let the craft die out.
I guess it's a case of playing God, of creating. And when I see one of these pieces, when I finally have one fully assembled and for the first time set the pendulum in motion and hear the beat of the clock, it's a wonderful feeling. The sense of order that I don't see in the world comes to life for me inside of a clock's mechanism. If you sit down to make a clock, as a clock maker, for money, you're an idiot. The preservation of them has its importance. The idea that someone is still making the individual pieces. The value of a human effort, I don't think, will ever end.
All other machines aspire to be clocks, even nuclear machines.
40 seconds.
Atomic clocks don't explode or even radiate. They just sit there, ruling earthly timekeeping. They provide the most precise time signal available. The most common atomic clock is called a cesium clock because it measures the resonant frequency, the vibrations of a stream of cesium atoms. They pass through a magnetic field, resonate, and that frequency is used to control a crystal which oscillates at more than 9 million cycles a second. The cesium atoms keep the frequency locked as accurately as anything yet known.
At the tone, Eastern Daylight Time, 15 hours, 54 minutes exactly.
The U.S. Naval Observatory operates about 70 atomic clocks with a master clock sampling the others that are online. The result is a master time signal broadcast by circling satellites. Navy ships depend on the system for global navigation. So precise, it would have been inconceivable when Harrison was tinkering away in England 250 years ago. The system is called Global Positioning, or GPS. It depends on a galaxy of 24 satellites that circle in synchronized orbits. GPS receivers, some so small they can be handheld, receive the signals coming down from orbit. The signals arrive at slightly different times depending on the distance to each satellite. By computing the time delays, the GPS unit figures out where on Earth, or sea, or in the air it is located and updates the information continuously.
A billionth of a second is the length of time it takes radio waves to travel 1 foot. So if you want to navigate to feet accuracies, 1, 2, 3, 4 feet, you have to know time to 1, 2, 3 billionths of a second and make sure all the clocks within the satellites are synchronized to within that level of accuracy.
GPS is turning up everywhere. Tiny GPS receivers help hikers find their way out of the wilderness. Soon they will indicate a train's position, helping avoid collisions. The timing signals are used to synchronize power and electrical utility grids. Some cars now come equipped with a talking GPS that will help you get unlost.
Next exit on the left.
Could a GPS system pass the ultimate test? Could it guide us down what is called the crookedest street in the world, Lombard in San Francisco?
We can see the icon on this mapping software. This is actually us driving down a street, and it's updated every 1 to 2 seconds.
The GPS unit did sense when the van turned the sharp curves, even though high buildings occasionally blanked out the satellite signals. Precision timing down to the billionths of a second helped us locate where we were on the old brick street.
Eventually we'll have two-way communication where we will actually, as we're driving along, we can be getting information such as on restaurants, hotels, gas stations. So we'll always know where we are and we'll always know what's around us.
Music engages the human mind in the most complex relationship with time. The creation of music seems to flow from the very core of our being.
So you can feel it. You can feel the tension. You hear the piano part by itself.
Jonathan Kramer teaches music at Columbia University and has written extensively about the central role of time in music.
You realize time is motion, time is change. Music is motion, and music is change. And when music has a strong sense of beat, people move to it. 1, 2, 3, 4, 1, 2, 3, 4. And that cyclical return to one marks a period of time that repeats over and over again. And people relate to that physically. So when you see a rock concert or a folk concert, people are often clapping their hands. And it's interesting the way they do it. They tend to clap on 2 and 4. 1, 2, 3, 4, 1, 2, 3, 4. But if they beat their feet, or if they're sitting on the ground and they hit the ground, they don't do 2 and 4, they do 1 and 3. 1, 2, 3, 4, 1, 2. There's something lower in the body about 1 and 3, and higher in the body about 2 and 4. When they want to do 2 and 4, they clap, but usually not down here, it's up here. It's 1, 2, 3, 4. It's amazing. This kind of cyclical feeling, bodily feeling, going over and over and over again with different nuance, is present in an awful lot of music in this world. And that's what musical time is all about.
Professor Kramer says that variations in timing are what add an essential human element to the playing of music.
I wouldn't say that performance is all in the timing, but the timing aspects of performance seem to me to carry a huge amount of the emotional meaning that a performer is trying to project.
Right. It's a very powerful part of what we do, no question. Yeah.
A cellist can play a Bach solo in a number of different ways just by changing the timing.
What I've put in the computer is the notation that Bach wrote. It's also the notation that Norman plays. He sets this on his stand, he looks at it, and he interprets it. What the computer does is not interpret it, but simply play it. Every note comes out exactly the same duration as every other note. All nuance is gone. And for me, anyway, it's not very pleasing, at least not after it goes on a bit. Let's listen to it. In the history of the computer, this is a great accomplishment to get a computer to play from music notation like this. Now that we're used to it, we see the limitations, we hear the limitations. I took the notes which should be long and made them short, and those that should be short and made them long by using a 6:7 ratio. And let's see, my basic speed, okay. So this one really does sound a little bizarre, but not uninteresting. I can't swing my body to this one so easily, but it's still not chaotic to listen to.
This music needs a pulse, a human beat, not the absolute ticking of a metronome.
But you know what happens with what performers say about metronomes? They say, we can't stand them, we hate them. They always want to throw their metronomes out the window because the metronome is telling them, if you want to play with me, you've got to do it exactly evenly. And they don't want to. They can't. They hate their metronome.
When audiences settled into their seats around the first of the century to watch the new art form, movies, they discovered time expanded and contracted in surprising ways. The surprise has continued. Individual frames of film snapped one at a time over hundreds of hours can make even dreary dirt as exciting as watching, well, grass grow. Hundreds of frames exposed each second reveal a world of time never before seen. Film can make a pretzel out of time in numerous ways. Film has also treated time as its subject, the keeping of time, the spending of time, traveling through time. The Time Machine was the first successful sci-fi film about time travel. It is based on the H.G. Wells novel in which a scientist travels into the future and witnesses the degeneration of humankind.
Going the wrong way. Back.
Hollywood went on to make more movies about time travel. A few were wildly successful at the box office. Back to the Future traveled Back to the Future 3 times and can now be experienced as a wild, high-tech tourist ride at Universal City in Southern California. The magic of Hollywood. Kids and parents alike pay their money and take their chances on being eaten alive by a dinosaur 70 million years out of its time. If we traveled back in time a few hundred years, we might hear a poet comparing time to an arrow. In the arrow of time, the point meets the future, the middle is the present, the tail remembers the past. It doesn't take an Einstein to figure it out. At one time, it did take an Einstein to figure it out. Albert Einstein, born 1879, died 1955. At the age of 26, Einstein published his first major paper about relativity. It radically changed the basic concepts of physics. Almost a century has passed since Einstein's first paper. To help illustrate his thinking in the most modern way, we rented a corporate jet. As the pilot dives to make a run at the camera, he turns on a light on the wing of the jet. Without thinking about it too much, it would seem natural that the light shining from the oncoming jet is moving at us faster than light reflected from objects that are not moving. But Einstein concluded that nothing moves faster than the speed of light, 186,264 miles per second, and all light, including the light from the jet, is traveling at the same speed. Something had to give. Albert's genius was in realizing that time is sort of a stretchable rubber band. Its rate depending on the speed at which one clock is traveling compared to another. Since the jet is moving so fast, the clocks on the plane are running, compared to clocks on the ground, just a teensy bit slower. Somewhere on the order of 1/1,000,000th of a second slower. Even when we are going about as fast as we can go, we are only inching along compared to the speed of light. Perhaps that's why Einstein's concepts are so hard to fathom. They are completely outside our realm of experience.
8, 7, we are go for start. 5, 4, 3, 2, 1. Booster ignition and liftoff of Atlantis on a mission to study planet Earth.
Astronauts travel 30 times faster than corporate jet pilots. Joe Tanner traveled 4.5 million miles when he flew in a shuttle mission in 1994. Joe has an identical twin brother, David.
After the space flight, now I am 321 microseconds younger than I was before the space flight. I guess I don't feel all that much different.
Well, I used to have a mustache like yours, but everyone says I look so much younger without it. I shaved it off so I could catch up on those 321 microseconds.
321 microseconds.
Joe and David are now living examples of what physicists call the twin paradox, a result of time dilation. The question of why time slows down for one traveler as he approaches the speed of light, but not for the twin who stayed behind. As fast as the shuttle is going in orbit, it's only going a tiny fraction of the speed of light. That's why Joe is only 321 microseconds younger. Again, it's a problem of human perception. Joe and David and the rest of us have only experienced a tiny slice of time and space. Beyond our realm of the senses, our Umwelt, things move incredibly faster and incredibly slower.
There once was a woman named White who traveled much faster than the speed of light, and when she departed her house one day in a relative way, he came home the previous night.
If Joe had had some real power under the hood of that shuttle, he might have been able to blast faster and faster to almost light speed to the center of the Milky Way and back. Arriving on Earth after what to him would have been a 40-year flight, he would find that his twin brother David had died 60,000 years before his return. One way of regarding this trip is that the twin astronaut has time-traveled into the future. Going forward in time at near the speed of light is relatively easy. Traveling backward in time seems all but impossible now, but it isn't ruled out by Einstein's theory. If Joe Tanner in his super shuttle wanted to go back in time, he would have to locate a black hole. And not just any black hole, a special black hole connected to another light years away. The resulting tunnel in time and space is called a wormhole.
It's an open question right now of whether these wormholes exist. If under certain strange conditions, the gravitational field can become repulsive rather than attractive. Right now, of course, the gravitational field is attractive. If I raise, for example, a book and drop it, it falls down. That's attractive gravity. If gravity can ever become repulsive so that books go up rather than down, it can happen under certain, we know, extreme conditions, which have never occurred here on Earth or even in an earthly lab. Then what happens is you can use this repulsive gravitational force to, so to speak, create one of these wormholes, knock a hole in space, so to speak, to create a wormhole, just like we drill a tunnel through the Earth.
Suppose a wormhole does twist time as well as space. Suppose NASA engineers were able to keep two wormholes open and connected using a repulsive gravity source. Suppose the super shuttle could navigate through the connecting tunnel. Suppose they found Elvis out there. Suppose. Cosmologists do a lot of supposing.
Now, one of the theorems that was proven many years ago is that if you create a wormhole in a region of space where it never existed before, you must also twist time in such a way that time travel becomes possible. In other words, not only do you have created a hole in space, you must also have twisted time around so that it becomes possible to return to your starting point in space-time before you left. You automatically create a time machine when you create a wormhole.
Professor Tipler and other cosmologists wonder whether the universe might somehow conspire to prevent time travel, due to an effect we can only imagine at this point. One cosmologist has brought up the problem of electromagnetic vacuum flux.
There once was a man named Joel who cheerfully entered a wormhole. He departed last May, and he hasn't came out until this day. Maybe vacuum flux destroyed the poor soul.
Electromagnetic vacuum flux? One theory holds that these small fluctuations looping over and over through time in the tunnel could be a big headache for stellar engineers trying to keep two wormholes open and connected. The result, they suppose, a horrifying feedback like some sort of cosmic squealing speakers. It would build up and instantly destroy the tunnel and the time travelers. But as long as we're supposing, suppose you could travel to the future and return to the past. What about a Las Vegas casino? Suppose you knew in advance when the jackpot fairy was going to smile on you.
Excuse me, ma'am. Would you like to go to the future and come back and know that you're going to win here on the slot machine? Ma'am?
Okay, forget which quarter slot machine will pay off. There would be gobs of money to make in the money markets. Well, maybe not.
You could take advantage of your knowledge for a couple opportunities, but once the people you trade with or the trading community know you're always right, two things will happen. Either they'll be very reluctant to take the other side of what you want to do, or they'll want to do exactly what you want to do, so you won't have much ability to take that kind of position in the first place.
This raises thorny questions about free will and predestination. In our everyday world of one-way time, time travel creates far too many paradoxes.
One of the problems that arises in time travel is what's called the grandfather paradox. The grandfather paradox says, if time travel is possible, then it ought to be possible to go backwards into time and kill your grandfather before he fathered your father. Then you've got problems.
You might tend to vanish if you shot your own grandpa. But Tipler says that quantum mechanics provides a theoretical solution. Quantum theory holds that each atom goes through all possible histories. Tipler asks us to think about such a universe, or multiverse. He supposes you would have killed a copy of your grandfather in another branching universe.
In that history, which you're now in, he does not father your father. You do not exist in that history. As a young man, anyway, what you have done is you have entered that history via the time machine. Now, if we could isolate ourselves, we would also be aware that we are existing in many of the universes. It's the very fact that we are, so to speak, anchored to one of these universes, because we are interacting all the time with the other atoms in this universe, that we're unaware of the other universes.
Professor Tipler, or at least the one in this universe, wanted to tell us more about what he supposes the future will bring. But we had suddenly realized we had completely forgotten about the clock. We have to bring this program to an end. We are just out of pine.